Hey everyone, I hope you're doing well. My name is Sarah Jane, and today I have a bit of a different type of video to bring to you. I'm going to try to do a technical overview. So, one night I sort of had a thought, what happened if I put the Fibonacci sequence inside of a smart contract on Algorand? And to give some context first, what is a Fibonacci sequence? So, it is a mathematical sequence where basically two of the previous terms um, add to create that current Fibonacci number. For example, if we can see in this box here, we have 1, 1 is equal to 2. 2, 1 is equal to 3. 3, 2 is equal to 5. 3, 5 is equal to 8, and so on and so forth. So we're going to put this inside of a smart contract and see what learnings we can get from it. So I've already done this, so I'm going to enter inside of my workspace. We'll do the recursive one first. And I thought to also show, inside of AlgoKit, this is how I got the smart contract already, so I could just code, which was super easy. But what you have to do is you enter your code space so you can build out your project and etc. So here we can already see my code. Now it's quite small. Firstly, we have our from AlgoPy library import. And I import three things: arc4 because this is a arc4 standard smart contract, so it stays within the standards in the arc4, so like for state or for ABI. We have global to access the global states, and uint64, which is an unsigned integer with 64 bits. So here we have our Fibonacci smart contract using arc4, which we have defined here, and we also defined our state variable, which is just n, and the nth term will store the Fibonacci number that we want to compute, so from our user. So here we have our at arc4.abi decorator, and inside here we have our allow actions no op. So that means this is only callable during a no op transaction. A no op transaction, in short, is just like a default transaction type. For example, there's others like opt-in, where you would opt into the smart contract, for example, if you had local state. But this one is nice and simple. We don't have any local state. And then we have our create equal to require. This basically means that this method here is only callable, or it can only execute during the time of the creation of the contract. So you can't call it again after the contract. This is just basically the contract initialization, and inside of it I don't have any logic, so I've just done a pass. So let's actually look at the proper logic. So I have this other method called compute underscore Fibonacci, where we pass through our uint64 data type. And this one basically computes the nth Fibonacci number recursively. So whenever you use recursion in programming, you have to have your base cases. So for example, here's the base cases for the Fibonacci. So if n is equal to 0, return 0. Else if n is equal to 1, return 1. And then this else gives us the recursive case of the fib n is equal to the fib previous term plus the fib's previous term. So for example, let's say we have n is equal to 3. So that's not 0 and it's not 1. Well, say we did the second one then. That would mean that it would be 0 plus 1, so the second nth term would be 1, I'm pretty sure. But we have the smart contract to do the calculation now, and we have it all in there. So let's actually build it out. So to do that, I'm going to do AlgoKit project run build to make sure I have the latest compiled. Nice, it's compiled there, and we can see our artifacts folder has given us all our generated, so we can see there's a lot of generated files. We just need to focus on the arc32.json one because I'm going to test this with LoRa because it's a great user interface to test with. But it's kind of cool to see that you can build in Python and it automatically compiles your clear and approval program, and we can get onto that in another stage. But for now, I'm going to reveal this in my Finder, and I'm going to do AlgoKit localnet reset because we're going to do the testing live. And this is just basically tidying up my Algorand blockchain privately, which I use Docker. And after this, I'm going to do AlgoKit Explore, which will take me to the web page of LoRa. Oh, and I also did want to show, like, Fibonacci is kind of cool because it's in nature and it's also in, like, galaxies. It's just a really cool sequence, and it's actually used for trading as well, which I'm sure some of you would know that more so. Alrighty, so I'm just going to X these off. So I'm in my local net. I'm going to move myself down here. Because I did local net reset, I'm going to disconnect and connect my KMD, which is the key management daemon, just to make it super easy for testing. And these are already funded, so fantastic. Now I'm going to go over to App Lab. I'm going to click Deploy New, and this is where I have the recursive Fibonacci. Let me just make sure. Yes. Perfect. And this is what we just compiled earlier. I'm going to insert that in the JSON app spec file. Let's call it recursive. And now we're going to call the create Fibonacci function. It already has the method in there automatically, the no-op transaction, and the sender, who is the one deploying, is the wallet I'm connected with already. So I'm going to add that, and I'm going to click deploy. Yay, it worked. So now, after this, we're going to click inside of our app ID, and we can see that the smart contract has one global state, which is the nth term. And if you also see here, when I click create Fibonacci, we can't call this method because we had it that it was on, that it was require, so it can only be done at the very creation of the contract. But let's actually use the method that we did right. So in here, we have our application ID automatically set, our method, our transaction, no-op, as well as the sender. Now, we do need to give it some user input, so the end term. So I believe I said 2 last time, so let's just see what 2 was. I forgot what I've put in already, what I said earlier, but we'll just add that in. You can also choose to simulate before sending. I like to just simulate to make sure it's working. But yeah, so 2 is 0 plus 1 is 1. So the second nth term is 1. Now let's do another number. Let's do 6. I think this one would be 8. Yep, we can see it there. Now the whole point, and I did do a write-up on this on Medium and on the Twitter X threads, that this was a great way to easily see how the opcode budgets work when you're building smart contracts. Now, opcode budget, in simple words, is just the mathematical effort. Because of course you can't just out of thin air use all these different calls and expect it to just work. There's obviously constraints, especially when you're building on a blockchain. So I already know what the number is. I believe it's 41. So the largest nth number, oh sorry, that's for iteration. For the largest nth number you can do for recursion is 7. And we can have a look here. And it works. But when we do 8 or above, we actually come into an error. And if you can read this here, the transactions failed because the local program cost was 700. Basically, the opcode budget for a simple smart contract on Algorand is 700. Now, of course, there's ways like opcode budget pooling and other ways that you can grow that opcode budget for your smart contract, but this one's very simple. The reason why it stops at the 8th end term instead of a lot bigger, like for example, spoiler, iterative is like 42. But the reason recursion is because you're calling, and I'll go back to the code, you're calling the method again and again, and this just stacks on the function calls. And so this is why it can't do as scalable or efficient as the iterative way. But since we've tested that now, why don't we look at the iterative Fibonacci number? So let me go here. The exact same thing we have to do is open our workspace. Alrighty, and now if we take a look at the code here, we are using AlgoPy and we import everything that we've already imported, except you might see there's a new one, uRange, which is basically for doing for loops in the smart contract. uRange also sounds very familiar for the Python one, for I in range, etc. It works the exact same. So here we've instantiated a class. We have two state variables this time. We have the nth, exactly like the other one, but I also wanted to show another way where you can also make a get method and you can get the result. Here we have, once again, the same, the allow actions no op, create require, and we don't really have anything inside of our create underscore Fibonacci contract. We just pass it through. So here we can see, oh, and also if anyone is interested, the arc4.abi decorator, that just allows to say that this method is callable by external measures, whether it's another smart contract or like in LoRa when we're testing. I'm not sure if I mentioned that yet. Okay, so here we compute the nth Fibonacci number iteratively. So I've initialized the first two. A is equal to 0, B is equal to 1. Now, here's where the real magic happens. We use for I in U range of n, and n is what we pass through by the user input. Basically, what is happening is we have A plus B, and they're added together, and we assign that to B. On the left-hand side, the value, not the recently updated one from this, but the other value is assigned to A, and so all the time the A holds the current Fibonacci number and B holds the next Fibonacci number, and it gets updated in this for loop, and it keeps going until we reach the nth term. Alrighty. At the end of that, we have A, because obviously A holds the current Fibonacci number that we want them to compute, and we store that into the result variable, and we return A. So in our get result method, we just basically return self.result for that instantiation. Alrighty, so now let's build it out just to make sure it's all updated. We just pull up our command line, AlgoKit project run build. And we can see that AlgoKit graciously has generated everything for us. So I'm going to reveal this one in Finder. Alrighty. And I'm going to go back to AlgoKit Explorer, or I can just click back onto the tab. And now we're going to deploy another smart contract. So we're going to click Create, Deploy New, and yes, this one. Next, we'll call this the iterative. We'll make that no op transaction call and deploy the smart contract. Great, we can see it's deployed at app ID 1002. We can click onto this, and this time we can see we have two global states, obviously for the nth term and for the result. Exact same story here. We cannot call this method again because we made it that it was only allowed to be called on the creation. And then we have our compute Fibonacci. So here, let's do straight away, let's do 8th, because we could not do 8 in our other smart contract using the recursive method. Move myself up here. So I'll add this in. I'm going to simulate so we can tell that this is going to work. So the 8th Fibonacci number is 21. I'm also just going to send it because I don't believe I sent any of the recursive ones on chain, but it's cool to see the live transactions happening here. Now, obviously, we can see the return value here, but let's just use the get method the get result method anyway, make sure it's working. So it sets up everything for us. We just need to call it, we'll simulate it, and nice. So that means it's going to work. And we can see that we get our get result method. So now let's obviously do the test of which is the largest nth term that we can call using the iterative approach, using the for loop. So if we go into here, and let's do 41. Let's send that transaction. Nice, we can see that 41 worked. Now if we do 42, we are going to hit that opcode budget limit again. This type of example made it very easy to test the limits of the opcode budget that you can use inside of a smart contract. Because, of course, when you're building your usual smart contract, especially when you're starting out, you're probably not going to hit that opcode budget limit, but it's something that's very important to be aware of, at least. Because the way you design your smart contracts then, algorithmically wise, or if you want it to be scalable in the future, it's kind of important to know these things. So yeah, this is kind of the experiment. I hope you enjoyed this tech overview. Please feel free to leave any comments or questions. You can also find me on X at goneanumtech or sarahjane.algo. And for anyone curious, I do have this code all open source. It's on my GitHub repository. I just put in that code that I went through there. Basically, I simplified the recursive one because I didn't think we needed to get the two get result methods. So in here, you can just go into the smart contracts, the Fibonacci recursive, and you can look at that contract right there. You can copy it, you can paste it into your AlgoKit init. And then I also have the iterative one here, which is also here. Okay, so thank you so much for watching this video. This is my first tech overview, so any feedback I really appreciate. And yeah, hope you have a great evening, and bye.